Okay, so now we're continuing on with our second video of week 5, where we're starting our three-part discussion on severe thunderstorms. First up, the ingredients for severe thunderstorms. So we can split up, there's four of them. We can split them up sort of 3 and 1 into the ingredients that any thunderstorm really needs. And those are moisture, some sort of lift or a trigger mechanism, as well as instability. And particularly what we need for severe storms is wind shear. We'll be going into all four of those in the rest of this video. So, to recall from past discussions in this course, recall sort of what really are thunderstorms in a meteorological sense. They're rapidly rising columns of condensing moist air, so it forms a cloud. But it's convection, so it's air moving upward, rising rapidly. And what they're doing from an energy point of view is that they're neutralizing the imbalance of steep lapse rates of large temperature contrasts in the vertical, as well as when you have warm, moist air near the surface, that's a large surplus of energy there relative to the rest of the atmosphere. And so it transports that heat energy and that latent heat energy from the moisture, transporting that energy upward and trying to restore a bit or act towards equilibrium. And so because it's moist, we need moisture. Because it's convective activity and it's rising air, we need instability for that to happen. And in order to kick this off, rather than it just being a spontaneous correction process, in order for it to actually form a discrete thunderstorm, we need it to hold off for a while and then some sort of lift trigger to start it actually going. So, again, we get our ingredients that we need for any thunderstorm coming up here. So moisture. You can sort of think of moisture as the food for storms. It's the main thing that they need in order to happen because they're clouds, they're convection. It's moist convection, so you need to have moisture. And typically this moisture comes in the form of a maritime tropical air mass. You need moist air in order to do this near the surface. Or even if you don't have a fully steady air mass, you need at least flow from a large warm body of water, which in the central United States is pretty much always the Gulf of Mexico. So you're always going to have flow coming up from the Gulf of Mexico, bringing moist air, not always saturated air, but air with a lot of moisture content up from the humid and warm Gulf of Mexico region. And moisture is important on both a large scale, talking sort of synoptic scale moisture, where we need to get the overall moisture transport and large air masses of warm, moist air. But also on the small scale is that if individual storm elements get cut off from the main moisture supply, they'll dissipate and go away. So there needs to be that continual supply of moisture in order for them to keep on going. The vertical distribution of moisture is also quite important, and maybe not quite for the obvious reasons, because you think storms are starting from the surface or at least low levels of the atmosphere. So that's where you actually are getting your moisture coming in that forms the cloud going up. But as those parcels move upward, they also have experienced something called entrainment, which is really just the term for the parcels of air that rise up into the storm mixing in that process. So it isn't a pure isolated parcel. It mixes with the air around it in the mid and upper levels. So some of that air is mixed into. So if that's dry, it inhibits the updraft, the rising moist air. But if it's moist, it can more readily continue on its way. Then we get to stability or instability. And stability is really the idea of what happens when you have a small displacement to a force. That's its general physics perspective. And when we talk about meteorological stability or meteorological instability, buoyancy, the vertical, is the key thing that we're typically talking about here. And that is really a function of density. So what does that actually look like in the atmosphere for what we talk about, stable, neutral, and unstable? When we're stable, that means we have a return to the original position when you displace it. You can think about it sort of like the diagram over here as a ball in the bottom of sort of a pit or a valley, that if you displace it one way, it will return back and sort of bounce back and forth. You'll get an oscillatory pattern because of the restoring force trying to bring it down to its original position. Neutral is sort of where it remains in its new position if you bump it over, or if you give it an initial velocity, it'll just maintain the constant velocity and not accelerate or decelerate. And so this is really the in-between case. It almost never perfectly lands on neutral. And one thing I didn't mention in stable is connecting it back to what we actually see in the atmosphere. A rising parcel is considered to be in a stable situation if when it goes up, it's colder than the air around it, because we're assuming the parcel maintains the same pressure, so that if the temperature is colder, that means it's more dense, which means it will tend to sink relative to the air. That makes sure it restores. The one thing to consider is that sort of the flip side happens if it's a sinking parcel. If the sinking parcel is warmer than the air around it, that means it'll try rising back up to its original position. That's what we consider stable. It tends to return towards its original position. It can overshoot just because of the way the forces work, but it'll always at least oscillate back to its original position in a stable regime. Neutral, again, is sort of the in-between case, remaining where it is. In the atmospheric sense, this means it's the rising partial maintains same temperature as the environment, so it's neither more or less dense than the surrounding air. Unstable is sort of the other way around. We think about a ball on the top of a hill, where it would accelerate away from its original position. In the atmosphere, this sort of means the flip side to what stable is. If you have a rising parcel that ends up warmer than the air around it, that means it's less dense and it's just going to keep on going upward. Flip side of that again, if you have a sinking parcel and ends up colder than the air around it, that means it's more dense and it's going to continue sinking even more. So that's unstable. It tends to accelerate away from the original position. So that's sort of the at a constant level perspective. That's the baseline of this. I'll go into sort of two applied views of instability when it comes to the atmosphere. So since instability in that sense means that a rising parcel is warmer than the environment, or sinking parcel is cooler, we don't have to just compare at each level and make an assessment. We can actually think about these as lines for at least some layer of the atmosphere and compare the slopes, because we consider a parcel to not just be something on its own, but it originates from a particular point in the environment and then travels off from there. So if they have the same starting point, you can just look at the slopes to compare where it ends up. And so we call this rate of change, or because temperature always decreases with height in the general sense, we actually have it be the negative to just clarify the sign. But that rate of change of temperature with height is called the lapse rate. And if the environmental lapse rate, the change in of observed temperature, if that decreases more with height than what the parcel does, where you take the initial parcel of air, keep it isolated, and force it, rather than just following what the environment, the existing temperature is. If the environmental lapse rate is steeper than that parcel's lapse rate, then that means the layer is unstable. And that's sort of the picture that we have over here, where our environmental lapse rate is steeper in this direction than our dry lapse rate, dry adiabatic lapse rate. We'll get to what that means in just a moment. But the key thing here is that after they start from the same position, with the environmental lapse rate being steeper than the parcel lapse rate, that means that the environment, once you get up to a certain height above where you started, is colder than the parcel, or the parcel is warmer. Warmer, less dense, it's already above, it will continue rising even more and accelerate away. So this is considered an unstable regime. I mentioned dry adiabatic. Hopefully that's not too scary of a term. Adiabatic really refers to that there's no heat exchange between the parcel and the environment. It just stays as an isolated unit with the type of air that it started with, and there's no heat exchange, but it does respond and equalize to pressure of its surroundings. So dry adiabatic is simply what it does. There's no moisture effects going on here. So it's before there's condensation, which in practice really means it's below the cloud layer. Moist adiabatic, on the other hand, is the pattern that happens to a parcel after you reach a condensation, after you've cooled it enough and raised it up enough so it decreases pressure, so it reaches saturation and starts condensing, and then you start getting latent heat release as it condenses moisture out. And this is actually because it reaches saturation and condenses. That's inside the cloud. So you can really think of a parcel having two different types of paths or different types of lapse rate, whether it's below the cloud or inside the cloud. Because inside the cloud, you're condensing, you're releasing latent heat, it's going to be less steep. There's going to be less of a decrease in temperature with height. So, sort of illustrating that, this red jagged line here is the environmental temperature. The blue line here to here is your parcel temperature. They start at the same point. Your parcel decreases along this steeper, this dry adiabatic lapse rate, up until it reaches its lifted condensation level, or LCL. The key point is that's just where it finally decreases to the point where it reaches saturation. From that point on, it goes on the less steep, moist adiabatic lapse rate line until it possibly intersects with the environmental temperature. And that's where it changes from, you notice in all of these cases, it's less steep, less steep, less steep. It's going to be, actually the temperature here, because of where it started, is less than the environmental temperature. So it's actually still cooler, so it would sink. Once it gets up here, it's actually reached enough buoyancy that it will start rising freely. So this is your level of free convection. This, though, this view breaks away from just this strict lapse rate view. We can only really compare the lapse rates once we have roughly constant lapse rates, so down here an initial starting point. If we want to take this more full view where we're comparing the whole parcel profile to the whole environmental profile, we need a slightly different outlook. And that's where we get to CAPE. So if we have the whole parcel profile and the whole environmental profile, instead of comparing just the starting point and then limiting ourselves to a certain slope, or just looking at a certain layer, we can look at the whole profile and just compare where the parcel is warmer, i.e. less dense than the environment, or cooler, that is more dense. So depending on which side the lines are on, we get two areas, typically. The positive area where the parcel is warmer, we call that the convective available potential energy. Actually, the math works out with the right constants to have this difference in temperatures convert to a energy quantity. And so this is this green area, this is the positive area where your parcel profile is higher in temperature than your environmental profile of temperature. This represents the amount of buoyant energy that's available for updrafts. And actually, if you go back to hopefully your high school level physics, you know that energy, so potential energy, if we convert it all to kinetic energy, that can give us a velocity. And so that actually, because it's buoyant energy for updrafts, if all of this cape, all this potential energy is converted to kinetic energy, that could actually give us an idea of what our maximum updraft strength of our thunderstorm is. But we can't just assume we just have cape. We also have this negative area, typically, where the parcel is actually cooler than the environment. And this is convective inhibition. It can be sort of physically thought of as a cap or a lid. It's a amount of energy that has to be overcome from any low-level parcels in order to break through and then reach all of this potential energy up above. So it sort of caps, or it puts a lid on convection until there's enough of a trigger, enough lift to break through it. Or sometimes if you want to cheat the profile, instead of needing that amount of energy from a trigger or lift mechanism, sometimes the profiles themselves change. Sometimes you get environmental air changing. So if you get cooler air blowing in a loft or warmer air near the surface, that can modify your profiles. Or you can also have your very surface temperature. If it gets warmer, if it gets more moist, that can shift the parcel profile over as well. Either way, in order to get convection to be realized, we end up having to get rid of that sin or overcome it through some kind of forcing mechanism. So to talk about that kind of forcing mechanism, or the trigger, we'll get to in the lift section. The one nice thing about CAPE, or another nice thing, rather than considering the more full sense of the profile, is it also just can give us a single number for every point. So if we have a model that represents the atmosphere in a full 3D sense, we can then turn every vertical profile into a single value and plot it in 2 dimensions on a map. And that gives us a really good picture of the amount of energy available for updrafts, available for thunderstorms. These are the kinds of maps that become really useful in severe weather forecasting. So, as promised, getting to the lift or convection trigger, we need something to get that process started on a smaller storm scale. Typical triggers for this are warm bubbles, where you get localized warm spots that allow enough buoyant energy to break through a cap. You also can have outflow boundaries or gravity waves, things that are disturbances that trigger enough density differences or enough vertical motion to overcome a cap again. Terrain, both sort of orography or mountain ranges, just general increases in height of the land surface, can force the wind upward, as well as just existing zones where you get convergence. And so if two wind patterns have to collide, if they're near the ground, they can only end up going up. So you get convergence, you get sharp upward motion, which can be enough as a trigger. Finally, fronts can also do this, similar to what outflow boundaries can do. The one thing that you may think, because it's upward motion, upper level forcing from troughs and ridges, you may think because, oh, that's upward motion, maybe that can trigger it. That's not high enough magnitude and isn't close enough to the surface to actually act as a trigger. So it does not work to have upper level forcing be a convection trigger. It still is useful, though, for thunderstorm development if it still can contribute, but not as a trigger. What it actually does is it helps the instability. It can modify the environmental profile, stretch it out, make some of your lapse rates a little bit more steep, so it's easier to overcome, or you get and stretch out and get a little more potential energy or more cape in there. So it still can contribute to thunderstorm development, just not as a trigger. So these are just some illustrations of sort of our warm bubble situation here, where you get differential heating. If you have a front, you can get warm air rising enough to act as a trigger, or mountains where you just literally forcing the air to go upwards because otherwise it's running into the terrain. So the final ingredient, again, this is the big one for severe weather. All the previous three are just ones that we need for moist convection or thunderstorms. Vertical wind shear is really what we need for severe weather. And vertical wind shear is a change in wind velocity with height. So velocity, speed, or direction. So speed shear is really what's the big needed one for severe weather, because that allows us to separate the downdraft from the updraft of the convection so it doesn't just fall on top of itself and kill itself off. If the updraft and downdraft are separated, that means that the storm can continue rather than die off quickly. And you're almost never going to get severe weather out of something that doesn't have this. And we'll go more into that in the next video, what kind of storm doesn't have wind shear like this. But you basically need this for severe weather to occur. Directional shear is a little bit more interesting, or at least a little more complicated, is that instead of just allowing the separation of updraft and downdraft, it creates enough dynamical patterns that allows rotation in these thunderstorm systems, which ends up leading to supercells, some of the most intense forms of severe thunderstorms, which is really where a lot of your hail and tornadoes come in. And again, I won't go into all the details about how you get these types of quantities, but you can get, similar to CAPE, you can get a single representative value. There's a bunch of different formulations to compare as well, that you can plot these things on a map. And I can see I'm going a little bit over on time, but I still want to bring all this together here at the end of this first video, is that looking at all these ingredients together, you can really do something called ingredients-based forecasting. And despite all the complexities of severe weather, and if you're interested, there's plenty of resource out there, or you can take upper level meteorology classes too, you can still really get a good enough idea of where the potential for severe weather is just by looking at where all these ingredients overlap and where they're the strongest. That's a basic ingredients-based forecasting approach. And so overall, you need moisture, instability, and lift for any kind of thunderstorm. Shear becomes really important for thunderstorms that last, which those are the kinds that end up typically producing severe weather. And all of these different moisture, instability, lift, and shear, we can come up with measures or different way of viewing or plotting these and analyze those plots to help produce a forecast. And that's what a lot of your severe weather forecasting meteorologists end up doing. So going up next, talking about actually some of the types and behavior of severe thunderstorms.